This is worksheet 8 of the States of Matter packet, and this one's going to be short, but really important points to make here. These are things that some students really struggle with, so I want you to listen carefully. Unlike a phase diagram, which we saw in worksheet 7, in worksheet 8 we're looking at a different type of a graph, which is a heating curve. Okay, now the heating curves also show phase changes, but I want you to look at the difference on the axes here. Okay, we've got time on the x-axis instead of temperature, and we've got temperature on the y-axis instead of pressure. So we're looking at kind of different things here. Okay, what I want you to imagine is, let's say I got a big pot of ice cubes sitting on my stove. Okay, a big metal pot, a bunch of ice cubes in it, and I turn on the heat real low. Just a little bit of heat energy. Okay, and so at the very beginning, my ice cubes, they're less than 0 degrees Celsius. They're very, very cold. Okay, but as that heat energy gets added, gradually I start to get sort of this slushy mixture of ice and water. And then as I wait even longer, I start to get just water. All the ice cubes are gone. Right? And then I wait longer, and that water starts to heat up and starts to heat up and starts to heat up, and eventually it starts boiling. And now I've got water still in the pan, but I've also got some steam coming off of the pot. And then if I wait long enough, which, you know, hopefully you don't do on your stove at home because you'll ruin your mom's pots and pans, but eventually you've got no water left. You've just got steam above the stove top. Okay? So that's what this graph is basically showing. All right? But I want you to notice something really interesting. This is very key. Okay? If you had a thermometer in that pot the whole time, you would notice something quite interesting. You would notice that at first, right, when you've just got the ice cubes, you start to very gradually add heat energy. Right? You put a little heat on the stove. Gradually, those ice cubes, the temperature starts to rise. And that temperature on that thermometer goes up and up and up until you hit 0 degrees Celsius, which is the melting freezing point of water. And then all of a sudden, the thermometer sort of seems to get stuck at 0 degrees Celsius. And that's right when you've got that mixture of ice and water. And you're like, well, I'm still applying heat energy. I haven't taken the pot off the stove, but for some reason, this temperature has stopped changing. That's weird. Okay, and you keep observing, and after some time, finally, you've just got water in the pot, and that temperature starts to increase again. It's not stuck at 0 anymore. And that temperature goes up and up and up and up. And when the temperature gets to 100 degrees Celsius, the melting, condensing point of water, right, you start to get steam rising off the top of the water in the pot, so you got this combination of water and steam, and once again, that thermometer seems to get stuck right at 100 degrees Celsius. It's weird because you've still got that pot sitting on the stove. You have not taken the heat off of it. Okay, and then eventually you get to the point where there's no water left in the pot and you've just got steam. And if you could trap that steam and continue to monitor the temperature of that steam, that thermometer, sure enough, would start rising again up past 100 degrees Celsius. Okay? It's weird, but that's what we're noting when we see, if you look at this graph, it starts to go up, and then it levels off. And then it goes up, and then it levels off, and then it goes up again. And it's always leveling off at the point of the phase change, where you're in between, you know, where you got ice and water, and then again when you got water and steam, in between two phases. And here's the really key thing that's happening. This is a very big point I want you to take away from this. When you're on that sloping region, the region of the graph where you're going up, when you just got ice, later when you just got water, later when you just got steam, okay? What's happening there is that heat energy that you're applying from your stovetop is being used to increase the motion of the water molecules. Remember, the way we measure motion of the molecules is temperature. So that's why we see that temperature on that thermometer going up and up and up. Okay, but whenever you get to one of those phase change regions, all of a sudden the heat energy is being used for something different. The heat energy is not increasing the motion of the molecules right there. Instead, the heat energy is all tied up, all busy, breaking the intermolecular forces between those H2O molecules, allowing them to move farther apart and change into water, and then later on in the next phase change into steam. And so when they're busy in the phase change, breaking apart those intermolecular forces, allowing for that phase change, there's not enough heat energy left over to increase the motion of the molecules. We're just breaking molecules apart from each other at that time. And so during those phase changes, we got to momentarily put a halt on increasing the temperature, on increasing the motion of the molecules, because the heat energy has to be used instead to break apart those forces. All right, and so that's a really important idea that we'll talk about more when we get to class next. And next, you're also going to take a look at a heating curve of this mysterious substance X down here. You're going to see the same general regions on the heating curve, and you're going to have to answer some questions about that heating curve. So I want you to apply the very specific heating curve of water to a more general heating curve of a mysterious substance X. But that will be when we get to class next.